Hello and welcome back to Let's Code Physics. We are in episode 2 in our series creating a gravity simulator. We took the bouncy ball code from our subscriber tribute and changed the interaction from being an elastic collision to being a gravitational force. At the end of the last episode, we successfully created the conditions for the Earth orbiting around the Sun. As you can see here in the animation window, the Earth is making its way almost a complete circuit around the Sun. We've got the Sun in the middle. We can't see the Sun move too much because of how much more massive it is than the Earth. So if we go back over here to the mass list, we see that the Sun is something like 1,000,000 times more massive than the Earth. And so our Earth did make a complete trajectory. Hooray, that's good. What we want to do is a couple things where we add in a few other calculations to this to try to get an idea of how the orbit is behaving. And then we're going to change this up. Instead of having it be the Earth going around the Sun, we're going to have two objects of roughly equal masses orbiting around each other to try to simulate the motion of a binary star system. So the first thing I'm going to do is I'm going to keep this as the Earth and the Sun for right now, and I want to add in a couple of calculations. There's two quantities that are kept constant during the motion of a planet around a star, really of any what we call a central force problem, where the force is only proportional to the distance between the two. Actually, there's technically three conserved quantities, but I'll leave a link to the third quantity in the description below because it's a little bit more complicated. But the two things that are kept constant are the energy and the angular momentum. Energy, you're probably somewhat familiar with. You've probably learned at some point in school. You probably heard at some point in school, whether you remember it or not is another story. You probably heard at some point in school that there's generally two types of energy. There's kinetic and potential energy. So what we're going to do here is we're going to calculate the total energy. And that's going to be the kinetic energy plus the potential energy. So we're going to start out with the kinetic. So we're going to say kinetic equals 0. So that we can then add the kinetic energy of each of the objects that are orbiting around in the simulation that we're running. So we're going to set up our IBB counter. IBB equals 1. While IBB is less than or equal to the number of... I think I said I was going to change that to bodies, but we may as well leave it with bouncy balls. Who knows? So kinetic energy, we're just going to add up the kinetic energy of each individual piece. Kinetic energy, as usual, is 1/2 the mass times its velocity squared. So I need to take the magnitude of the velocity of this object and then square it. So what we're doing is we're just taking each kinetic energy and adding to it 1/2 mass times its velocity squared. Wonderful. And then, of course, as always, I need to increment IBB by 1. So that's going to get me the total amount of kinetic energy. Then I need to get the amount of potential energy. And the potential energy is between every pair of objects in the orbit that we're considering. So we need to have two counters. So this is going to be the IBB and IBB1 or IBB2 counter type thing again. Let's call this thing potential equals 0. Oops, there we go. So we've got IBB equal 1. We'll do the same type of thing here. I could have made this a single loop, but for the sake of having kinetic energy calculation and the potential energy calculation, it's just as good to have it separate. So then we're going to have so I need to set up the second loop. I need an IBB2. And again, we don't want to double count anything, so we're just going to set this equal to IBB plus 1. So actually, I don't want this thing to run all the way to NBBS. I want it to run one short of that because when it reaches in BBS, there's not another one for it to increment up to. So there we go. So we'll say potential equals potential. Okay, I did spell that correctly. And our potential energy is going to be negative, and it's equal to the gravitational constant times the mass of the first thing times the mass of the second thing divided by the distance between the two. So we're going to take magnitude of the difference of their positions. So that's going to be bouncy ball list IBB.pause minus bouncy ball list IBB2.pause. Now that probably looks familiar because it looks a lot like the gravitational force. The potential energy and the force are always related. One is the derivative of the other one. So the only difference is that this distance between the two is to the first power in the denominator instead of to the second power. So it's just there instead of being squared. Okay, that should take care of that, and then we can report the total energy. So we're going to have this thing print the total energy to the screen. Total energy equals kinetic plus potential. There we go. Cool. So when I run this thing now, it should at the beginning of the code print out the total amount of energy. It should just print that to the screen. Unless, of course, I forget to increment my counters again, and then I run out of memory again. Well, my computer runs out of memory anyway. IBB2 plus 1, and then same thing here. Oops. Oh, I never actually set up a second while loop. While IBB2 is less than or equal to NBBS. Indent that, indent that. Oh, and I need a colon. That's why it didn't. Okay, yeah. Oh, no, I forgot to put in the counter anyway. Okay, there we go. And then, of course, I need to increment IBB, the original one. Okay, there we go. So I have 2 being set by 1. Then I have 2 keep on increasing. I have IBB keep on increasing. Okay, let's try that again. Okay, this time it gave me a total energy. So this is a calculation of the total amount of energy. I'm probably blocking that, aren't I? So this right here is a calculation of the total amount of energy of the Earth-Sun system. A few things to notice. Number one, it is a huge number because we do have both the mass of the Earth and the mass of the Sun. So we've got these things that are, 10 to the 24 times 10 to the 30. So those are quickly overcoming the 10 to the minus 11 in the gravitational constant and the large distance in the denominator. So it's a huge number. It's also a negative number. The significance of that negative number is that it means that we're in a bound orbit. It means that we are going to keep going around the sun. If this energy were to be 0 or positive, we would escape the sun. So you could simulate that by giving the Earth just a little bit more speed. So let's see here. What is the Earth? Where am I calculating the Earth's speed currently? Here's where I'm calculating the Earth's speed. So we're going to put in an extra line here. Let's say we give the Earth just, I don't know, let's say 5% more speed than it currently has. Let's see what happens here. Okay, so we still end up with a negative total energy. It hasn't changed by that much. So we can actually change this by a little bit more. Let's try giving this thing, 20% more speed. Okay, so you notice our number is still negative, but it's getting closer to 0. It's getting lower in magnitude. So let's try doubling the Earth's speed. Let's see what happens here. Okay, so here we end up with a positive energy for the Earth-Sun system. And what do you notice about the trajectory? It's no longer going around an ellipse. It's now shooting off in a hyperbola. And I'm not exaggerating about that. This Earth that we just gave double its speed to is never going to come back to the sun. We've all died of cold from here by this point in the orbit. This is why you don't see life on things that shoot away from the sun very far, because they don't come back to receive the radiation. Isn't that a cheery thought? So just by changing this, by giving us a little more energy, once we get a positive energy, the Earth shoots away, never comes back to the sun. We're going to comment that out. Only uncomment if you want the Earth to run away. There we go. Cool. So let's hope the Earth doesn't double in speed anytime soon. Not that we'll be around long enough to notice. Anyway, cheery start to the video, isn't it? Okay, so the other thing we can calculate is the Earth's angular momentum. The way angular momentum works is somewhat similar to this. We want to calculate the total angular momentum. And angular momentum is given by the special thing called the cross product. I don't want to get into too much detail about it here, but basically it's a way of taking one vector, multiplying it by another vector, and getting a third vector. I'll leave a link to a description of that, or a link to a reference about that in the description below. So let's say angular momentum equals 0. Now this thing is a vector, so I need to set it up as a vector. And then we can just repeat the same kind of structure here. In fact, why don't we just copy this thing, copy and paste. Well, instead of modifying the kinetic energy, I'm going to modify the angular momentum. The way angular momentum works is that it's the cross product of an object's position with its momentum. So we're going to take the cross product of BB list of IBB dot position. So the IBB object's position with its momentum. Momentum is its mass times its velocity. So we're going to take mass list of IBB times velocity list of IBB. So we are taking the cross product of this thing with this thing. Okay, cool. And then we're going to have it at the end print for us the angular momentum. And actually, let's do that here after the energy. So print total angular momentum. Ooh, I even got these to be the same number of letters. All right, always a good day in programming land. Angular momentum. So we should get out a vector. That'll be a triple of things. And that points in the z direction because the Earth's position is this way, its momentum is this way. So you take one, cross the other, and you get, well, it's heading this way to you, I guess. So it's going, no, so I'm being inverted, right? So I guess I have to use my left hand. So it's going this way, cross this way, goes that way, right? My video is flipped, so this is my right hand to you, right? So we end up with this angular momentum. I'm just curious about what happens to the angular momentum when we have the Earth run away from the sun again. Okay, I'm not sure that it crossed any special value. I mean, obviously it increased. I don't know that it crossed any special value there. Something to investigate, I suppose. Okay. So that's a lot of fun. So we can characterize an orbit by its energy and by its angular momentum. We can also now study some more interesting systems. So the Earth going around the sun is obviously important, but the sun isn't doing much. It would be nice if we had two objects that had roughly the same mass. So what we're going to do is we're going to start changing some of the values that we're working with. So I'm going to save this under a different name now. And we're going to call this binary stars. So it happens in a binary star system, and there's actually a lot of binary star systems out there, is that you have two stars. They're not necessarily of the same mass, but they're I don't think one is usually gargantuanly larger than another. I could be wrong about that. But, you know, they're two stars, and they notably orbit around each other. And that's really interesting because that can produce interesting, electromagnetic interference, gravitational waves, all kinds of stuff that we are interested in looking at. So we want to be able to model these two things going around each other. So what I'm going to do is I'm going to change the masses. We're going to make this much simpler. We're just going to give these things a mass of 1. So we're working in some artificial units here. Obviously, these things don't have a mass of 1 kilogram. We're saying 1, we'll call it a star mass. So let's call this one star 1, and this one star 2. Okay. And so what I'm going to do is I need to change some of the other values. So for example, I don't want their radii to be millions of meters anymore. What I'd like for them to be is more manageable, some more manageable numbers, so that we're not worried about all this scientific notation stuff. So what I'm going to do is I'm going to make the radius proportional to the mass. Just so that as we make one larger or more mass or less mass, it'll also become larger or smaller. And so I don't think I'm going to need this times 10 anymore, but we will see. And let's make one yellow, and let's make the other one red, maybe. Yeah, so let's see. So my initial condition, let's put one of these at 1. and 1, 0, 0. Actually, let's leave 1 at the center and at rest. Let's put number 2 at 1. Let's give it a radius also equal to the mass. Again, just to, make it proportional. We'll get rid of this times 10. I think that'll work out. I guess we'll find out. Oh, actually, that won't work out, will it? Because then this thing is they're going to be as far apart as they are large. So let's maybe take radius and let's say times 0.1. Here we go. It's all just for scale for animation anyway. And so I want to give this thing, I don't want this thing to look like the Earth anymore. So let's give this thing a color of, let's make them both yellow. Sure, they'll be similar suns. Okay, so we don't need this calculation anymore. I can just go ahead and set the velocity. I played around with some values earlier. The velocity I'd like to use first is 1/2. And now I'm using these artificial units, so what I'm going to do is set g equal to 1, right? Just so that way, everything's in sort of natural units. G is equal to 1, the masses are equal to 1. It's all kind of nice and simple. And I think I probably need to change my dt to something smaller, but we'll see. Okay, so I set the two masses equal to each other, and I've put one of them out at 1, given it a... I do want to give it an... I do want to give one of them a different speed. Let's give this one a negative 0.5. You'll see why I want to do that in a second. Okay, so let's run this thing and see what we get. Okay, wow, that is going really fast. Do not adjust your YouTube sets. Let's turn this rate statement down a little bit there. There we go. Still a bit much. Okay, how about we also decrease the dt, because that orbit is a little bit jagged, I think. Here we go. Much better. Okay, so what we get is these two things. So these are now equal masses, so they're exerting the same force on each other. And of course, the system's got to be symmetric, right? So they're making ellipses that are the same, right? The two masses are symmetric. They're starting out with opposite velocities. And so they're going around in these ellipses that are the same. You can even rotate it. You can see, they're all nice and in one plane together. Of course, conservation of angular momentum. They're getting faster as they get closer in. You also notice, again, the total energy is negative, and that means this is a bound state. That means that these two things are going to be rotating around each other. I bet you if I resize this, ooh, I can see both of them at once. That's great. So cool. So that makes, these nice two same ellipses. Let's do this, though. Let's up the speed just a little bit from 0.5 to 0.7. So let's see. And we're going to keep the speeds the same. You notice that these two things are rotating around each other. Here's what happens if I make the speeds different. If I make those velocities different, is that you get this much more interesting pattern, but now they're sort of traveling off. And, they can certainly do that. We're all, every star is moving around in the galaxy. But, this makes the animation difficult to see. So I'm going to try to keep it to where they'll orbit around each other instead of shooting off somewhere, just so that the animation window doesn't become tiny. But definitely feel free to play around with this. This is reminding me of my days on a Spirograph when I was a kid, which I might have for somebody for Christmas. Shh. He's probably not watching this. Let's see. So what do I need to change? I need to change this to a negative 0.7. All right, let's run this guy. Okay, so I increased the speed. You notice what happened to the energy is the energy went from being a negative 0.75 to a negative 0.51. So I'm getting toward a different value of energy, and that's producing a different orbit. In fact, these two things are almost going in a circle now. They're almost going in overlapping circles with each other, which is pretty cool. Let's see. So that's pretty neat. So again, obviously the conditions have to be very fine-tuned to get that circular motion. Let's try increasing that speed just a little bit more, though. Let's see what happens if I make this thing. We went from 1/2 to 0.7. Now let's try a 1.0. You notice that the energy here, we've just hit energy equals 0. So at energy equals 0, these two things are able to scatter away from each other, and they just barely have enough energy to get away. We call this parabolic motion. It's got to be an exact total energy of 0, where the kinetic energy exactly cancels the potential energy, and you get these parabola-shaped orbits. So if I make this even just the tiniest bit smaller, right? So 0.999 is smaller than 1, just by a little bit. Even if I make this a little bit smaller, my energy is negative. And even though these things, well, they're about to prove me wrong, aren't they? These things scatter away from each other. You can tell they're kind of curving downward a little bit. All right, maybe I made that a little too close. Let's make this a 0.99. I went off script. That's what I get for going off script. So you notice the energy is negative again, and these things, they start to move away from each other. They are slowly curving up, very slowly. Very slowly. Come on, y'all, don't prove me wrong here. Y'all have a negative energy. That's a bound state. Okay, let's try making them 0.9. This is what I get for going off script, is that the... Okay, negative 0.19, smaller. You can see they start to make this scattering motion, and then they get caught because the potential energy overcomes the kinetic energy. So that 0 energy cutoff, that's the difference between these two. I suspect these two didn't work out because they're going out really, really far, and either the code isn't capturing that, or it's making an error in the total amount of energy. Okay. So let's try a couple other things. Let's try changing their masses. So let's make the first one, let's try making it half as big as the second one. So let's try, where's my mass list? Here we go. Let's cut this one in half. Now, in order for them to, stay in, one nice little box, that means this thing needs twice the speed of the other one. So we're going to have this one have a velocity of 0.5, and this one have a velocity of 0.25. So star 2 has twice the mass of star 1, so that means star 1 needs half the velocity, or excuse me, needs double the speed of star 2. There we go. Again, you notice we get the negative energy if they're in a bound state, but because now one is more massive than the other, and now you see why I put in that business about the radius and the mass, is that the lighter one, the less massive one, gets a much broader ellipse than the central one does. So what we're seeing here is the beginning of what we have with the sun and the earth is the extreme case. So the sun is so much more massive than the earth. Its wobble like this is much, much smaller. Now these two are passing sort of dangerously close to each other. Of course, they're not going to collide because they're going to keep, running in this pattern here. What we can do, we can take this, and we can make this an even bigger extreme. So let's try changing their velocities a little bit. So let's give one of them a velocity of 0.35, one of them a velocity of 0.7. And what you get here is the ellipses no longer intersect with each other. So this is, again, sort of building up to the example of what we have with the sun and the earth, where, the larger one is not moving as much, and it's moving so little that its orbit is completely inside the orbit of the smaller one. So we do make the sun wobble ever so slightly. I think Jupiter makes it wobble more than we do, probably. Hard to tell because it's farther away, but I suspect it has a bigger effect because it's so much more massive than we are. If Jupiter were just a little bit larger, it would have formed a star, and we would have had a binary star system in our solar system, and the Earth would have been in between them. And let's just not think about those things, right? Yeah. So anyway, this is the type of fun thing that we can do with this simulation. We can play around with the masses, we can play around with the velocities, and get all these neat different orbits. So that is a lot of fun. What we are going to do next time is go up to the next level. We're going to add a third body to this system. We're going to see what happens when we've got three things interacting, we won't get these nice clean ellipses anymore. It'll be something much more interesting, much more like back in the days of the spirograph. So thanks so much for watching. See you next time. Bye-bye.